In this chapter, we'll talk about transformations of stress and strain. We have already calculated stresses about specified areas passing through a certain point. In this chapter, we will consider the most general state of stress at a given point. You can see in this figure, for example, a system that is able to measure linear strain by a strain gauge. In this course, we will see how the components of stress are transformed under a rotation of coordinate axes. We have already seen that the most general state of stress at a point may be represented by 6 components. So if you take the following control volume, you have several faces. You have 6 faces, and each face will be subjected to normal stress and to shear stresses. And since as we discussed before, we have that tau xy equal to tau yx, tau yz equals to tau zy, and tau zx equals to tau xz. So this is why we need just 6 components to represent the stress at a certain point. So which are sigma x, sigma y, sigma z, the normal stresses in the 3 different directions, and the shear stresses tau xy, tau yz, and tau zx. Now, as we have mentioned also before, concerning the subscript of tau, the first subscript will represent the direction normal to the face containing the shear stress, and the second subscript x here will represent the direction of the shear. And always the positive convention for a shear is the following. So if I say tau yx is positive, then if the normal to the face is along positive y, then tau yx is positive for tau yx along positive x. On the other hand, if I take the bottom face, or the bottom face here, the normal vector will be along negative y direction. This is why the positive tau yx is in the negative x. So this direction, tau yx on the bottom face, is considered to be positive. The same apply for all faces. So for this face, the positive convention for tau xy is upward, because the normal vector is along positive x. So tau xy is positive when the shear is along positive y. Now, the purpose here of this chapter is to deal with different frames. What if I rotate the frame? I want to deal with a new frame. Let us say I did a rotation here, as you can see in the following figure. I did a rotation of axis. So I am interested now in new axis, x prime, y prime, z prime. And I want to determine the state of stress relative to this new frame. How can I deduce the components of stress from my previous frame? So if I know sigma x, sigma y, sigma z, tau xy, tau yz, tau zx, how can I deduce the normal and shear stresses in the new frame? So this is what we will develop in this chapter. To start with, one of the main types of stresses is plane stress. When we talk about plane stress, it's the case where we have 2 faces of the cubic element that are free of stresses. So just you can say that all forces and stresses can be defined in one plane. In this case, for example, if you look at the following figure, along Z, you don't have stresses. So you have sigma Z, tau Zx, and tau Zy equals to 0. And then you only have three unknowns to deal with to determine the state of stress, which are sigma x, sigma y, and tau xy. Let us take examples of plane stress. If you look at the following case, you have a thin plate that is subjected to forces acting in the plane of the plate. So in this case, if you study any small element, you will just have stresses, normal and shear stresses along the plane of the plate. So this is the case of a plane stress. Also, whenever we have a free surface that is not subjected to external force of a structural element or machine component, we can say that it's subjected to plane stress. So any free surface not exposed to external forces can be treated as plane stress case. Now, let us try to derive relations between stresses in different frames. So let us work first with the case of plane stress. Consider the following element. The following element is subjected to stresses in xy plane, no stresses in z. So we only have then to define the stress state of this element at point Q is to just find sigma x, sigma y, tau xy. And knowing these stresses, we want to deduce what will be the values of stresses in another frame, x prime, y prime, z prime. So the idea is the following. I did a certain rotation, as we mentioned before, and now I have a new cut for my faces, for my elements. And I want to determine for these faces, what are the stresses they are exposed to? I want to find normal stresses and shear stresses. So the idea will be to take a small element that is containing both types of stresses in both directions. How? Instead of taking a cubic, a square element, I can take a triangular element. And we'll see then how by doing the equilibrium analysis, we can relate the stresses in different frames. So the idea is the following. If I take a triangular element, on these faces are one parallel to y, one parallel to x. While I have one of the faces of my triangle that is perpendicular to x prime, so parallel to y prime. So in this case, when I take the equilibrium of this element, I will be able to relate stresses in x and y to stresses in plane y prime, normal and along y prime. Okay, so the idea is the following. Let me put all forces acting on this triangular element and then apply equilibrium relation. Sum of x prime equals 0 and sum of f prime equal fy prime equals to 0. To start with, as we mentioned, so for this face first, for this face, you have the normal stress is along x direction. So the force in x acting on this face is sigma x times the area of this face. The area of this face is determined from the figure here. You know the area of the inclined face of the triangle, and you know that this area is doing the angle theta with the face parallel to y-axis, because as you can see here, when you do the transformation, when you rotate an angle theta, the angle between x and x prime is equal to theta. And therefore, you can say that the angle between y prime and y is also equal to theta. So this face here can be related, the area of this face can be related to the area, the red area, by saying that delta A times cosine theta will give me this area. Why? Because I have the same width along Z, but if I compare the sides, so I compare the two sides. This is the side of area delta A, while the side of the area parallel to y-axis is delta A cosine theta. Because this side here is equal to, if I call this side L and this side W, delta A is equal to L times W, while this area here, the other area, this one, is equal to this distance, which is L cosine theta times W. So LW times cosine theta. L times W represents the area delta A. I can do similar analysis for this area, which is in plane XZ. So as we already mentioned, the width is the same for all areas, but here the length of this part is L sine theta. So when you multiply by the width omega, omega L will give you the area delta A, and then the area of the face parallel to XZ plane is equal to delta A sine theta. So now, when you do the analysis of forces, here you have the force normal to face parallel to plane YZ. Then you have to multiply sigma x by the corresponding area, which is delta A cosine theta. Now, concerning tau xy, as we mentioned, for this surface, the positive convention for tau xy is downward because the normal vector is along minus x. So tau xy positive is directed along minus y. And you multiply by delta A cosine theta, which is the area of this face. So now you have calculated the normal force and the shear force relative to your first area that is parallel to plane YZ. You will do the same for the area parallel to plane XZ, this one. You have the normal force will be sigma y times delta A sine theta, while the shear force will be tau xy delta A sine theta. And for your inclined face has a normal vector along a positive x prime. So the positive shear will be along positive y prime. So this is tau x prime y prime. The corresponding shear force in this plane is equal to tau x prime y prime times delta A. And the normal force is equal to sigma x prime times delta A. So now you have all forces acting on your element. We presented all forces acting on the element, and since we have equilibrium of the structure, then we have sum of fx prime equals to 0 and sum of fy prime equals to 0. So now what we have to do is to project forces along x prime and y prime. To start with, let us consider some of forces along x prime. You have first, of course, this force, sigma x prime times delta A. Now, for this one, so for this force, you have to do projection. First, it's negative along x prime. So if I consider this is my x prime direction, if I project this force along x prime, I get a negative projection. And since the angle here between the two is theta, so I should do sigma x delta A cosine theta times cosine theta. So this is the projection of this force on x prime. Now I move to the second force here in this plane, this one, the shear force. For the shear force, also as you can see, it has a negative projection. And because you have the angle here is theta, so we said that this is theta. Because this is theta, this will be here 90 minus theta. So when you project on x prime, or you do cosine 90 minus theta, or you do sine theta. And since it's a negative projection, it's minus tau xy delta A cosine theta, which is the force times sine theta. We are done with these two forces. We still have these two, the projection of these two forces. Again, this is x prime direction. X prime is doing an angle with the horizontal of theta. So when you project now this force, okay, when you project the shear force along this plane, you should multiply by cosine of theta. And since the projection is in the negative direction, so when you project on x prime, here this is x prime, this is your force. So this is our force like this. When I project it on x prime, it's a negative projection. This is why you can see here minus tau xy delta A cosine theta times cosine theta. Now for the normal force, as we mentioned, the same analysis here. This is 90 minus theta. So if you want to project it on x prime, you have also a negative projection. So you should do minus sigma y delta A sine theta times sine theta. And just here, sorry, this was when we did the projection of tau xy, it's here. We are projecting on some on x prime. Okay, so now you have projection of all forces on x prime equals to 0. You got your first equation. In this first equation, you will be able to express sigma x prime function of the stress state in plane xyz, or in plane xy here, because we are considering 2D plane stress. So as you can see here, this equation will give you sigma x prime as a function of sigma x, sigma y, and tau xy. So if you know the state of stress in plane xy, then you will be able to determine the state of stress along sigma x prime. Okay, and now if you want to do the analysis for sigma y prime, all you have to do, you can consider just the same relation, but now instead of considering an angle of rotation theta, you can take the angle of rotation theta plus 90. Theta plus 90. So if you replace in this formula theta by theta plus 90, then you will get sigma y prime. Because if I rotate from x an angle of theta plus 90 degrees, I will get the state of stress, okay, along y prime. And therefore you can deduce easily what is sigma y prime formula. Now, if we move to sum of forces along y prime equals to 0, same idea, we do projections. So all we have to do is to consider this direction, y prime. We project all forces along y prime, and we say because of equilibrium condition, sum of forces along y prime equals to 0. So first, you have this force is perpendicular to y prime, no projection. You have the force along the plane here which is plus tau x prime y prime delta A. This is the first term of your equation. Now, if you project this force, the angle with y prime is 90 minus theta, and it's a positive projection on y prime. So this is why it's plus sigma x delta A cosine theta times sine theta. Now for this force, it's doing an angle theta with y prime, and it has a negative projection. This is why we do minus tau xy delta A cosine theta times cosine theta. And finally, the same idea for these two, for tau xy and for tau, sigma y. For sigma y, it's a negative projection, and the angle is theta, so it's minus sigma y delta A sine theta cosine theta. While for the shear, for this force, if you do the projection, it's positive, because as you can see here, this is my shear stress, this is my y prime. If I do the projection on y prime, I get a positive component, and because the angle is 90 minus theta, then I do plus tau xy delta A sine theta times sine theta, and summation of these projections should be equal to 0. So as you can see here, sum of forces along y prime equals to 0 will allow us to get tau x prime y prime function of sigma x, sigma y, and of course of the angle theta. So for each angle theta, you have a certain relation. So sigma x, sigma y, tau xy, and let us specify also that theta can be variable. So I can change theta as I like. For a certain specific value of theta, I can just express function of sigma y, x, sigma y, and tau xy. But theta also can be a variable. So this is why we can consider that we can express sigma x prime and tau x prime y prime function of these four variables: sigma x, sigma y, tau xy, and theta. So now, in summary, if we rearrange our terms, then we can say that we were able to determine an expression for sigma x prime and for tau x prime y prime. Delta A will be simplified because you have it in all terms. So at the end, you get that sigma x prime is equal to sigma x cosine square theta plus sigma y sine square theta plus 2 tau xy sine theta cosine theta. And tau x prime y prime is minus sigma x minus sigma y sine theta cosine theta plus tau xy times cosine square theta minus sine square theta. Now, we will try to get simpler relations. And here you have cosine square, you have sine square, you have product of sine and cosine. So we'll try to use the trigonometrical rules in order to simplify our equations. Okay, the idea is we will try to implement, if you want, the angle 2 theta, because we have trigonometrical relations between the product of sine cosine and between cosine square and sine square and the double of angle theta. The trigonometrical relations are sine 2 theta equals to 2 sine theta cosine theta, cosine 2 theta equals to cosine square theta minus sine square theta, and cosine square theta equal to 1 over 2 times 1 plus cosine 2 theta, and sine square theta is equal to 1 over 2 times 1 minus cosine 2 theta. If we use these trigonometrical relations, we can end up with simpler expressions for sigma x prime, tau x prime, y prime. And in this case, we can demonstrate that these values, okay, can be the coordinates of points on a circle. Why? Because here you have sigma x prime equals to sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta, and tau x prime y prime equals to minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cosine 2 theta. You know that for a circle, the equation is is exactly similar to this expression, because you can say then that if I take this side, this term to the other side, this is the coordinate of the center. The center of the circle will have coordinates as sigma x plus sigma y over 2 and 0. And you have that here you are multiplying these terms, okay, by cosine of a certain angle and sine of this angle. Okay, so let us see how we can demonstrate that this formula can be written as the equation of a circle. Okay, so to do this, first, if you consider this expression, okay, take this term to the other side, and then square both terms. Okay, square both terms. If we square both terms, then we'll have the following. When you square both terms and you do some simplifications, because using cosine square plus sine square equal to 1, you will end up with the following relation. Sigma x prime minus sigma x plus sigma y over 2 square plus tau x prime y prime square equals to sigma x minus sigma y over 2 square plus tau xy square. So we can deduce that the coordinates, representing the stress state can all be placed on a circle, okay? And this circle is characterized by a center of coordinates sigma x plus sigma y over 2 and a radius of radical. So this is r squared. You know that the general equation of a circle is x minus a square plus y minus b square equals to r square. So by comparison, if you look at this formula relating the stresses, you can say that the center of the circle will be of coordinate sigma x plus sigma y over 2 and b is 0. And you have that the radius is radical of sigma x minus sigma y over 2 square plus tau xy square. This means that I was able to find a simple relation between stresses in different directions. Okay, all I have to do is after getting these relations and implementing the angle 2 theta, I can say, let me rearrange my terms. If I take this term to the other side and I square both terms, if you do the expansion, it's very simple. Just you do this term square. So you have a plus b square equal to a square plus 2ab plus b square. And you do this term also square. You will see a lot of simplifications because cosine 2 theta square plus sine 2 theta square is 1. So this will give you the term sigma x minus sigma 1 over sigma y over 2 square. And squaring this term and this one will give you sine square 2 theta plus cosine square 2 theta times tau xy square, which is equal to tau xy square. And the terms 2ab will cancel out because here, if you do here, for this term, you have plus 2 times this term times this one. So plus 2 times sigma x minus sigma y over 2 cosine 2 theta times tau xy sine 2 theta will give you exactly the opposite term of 2ab of the second square. So here, when you do 2ab here, you have a minus before it. You have a minus before it. So we'll get minus 2 times the same, exactly the same term. Sigma x minus sigma y over 2 sine 2 theta plus times tau xy cosine 2 theta. So you have exactly the same combination. You have the term sigma x minus sigma y over 2 times tau xy, and you have cosine 2 theta and sine 2 theta. So because these terms are all the same, but the sign is different, here it's plus, here it's minus, then they will cancel out. And you will end up with the equation of a circle. Now, as we already mentioned before, you can easily deduce the expression of normal stress along y prime by just replacing angle theta here by theta plus 90, because to rotate from x to y prime, the angle will be theta plus 90. So if you replace here theta by theta plus 90, you will get sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times cosine 2 theta plus 180. And we know that cosine 2 theta plus 180 is equal to minus cosine 2 theta. So here for sigma y prime, you will have minus sigma x minus sigma y over 2 cosine 2 theta. And the same for this term. This term will give you plus tau xy sine 2 theta plus 180. And sine 2 theta plus 180 is also equal to minus sine 2 theta. So you can easily then deduce the expression of sigma y prime. Sigma y prime is sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 cosine 2 theta minus tau xy sine 2 theta. In this way, you were able to find a relation between the stress in plane x prime y prime that is rotated about z axis with an angle of theta relative to xy plane. So now, until now, we have seen that state of stresses can be plotted on a circle, and this circle has a certain center and radius known, that we can calculate function of sigma y, sigma x, sigma y, and tau xy, which is the stress known, the state of stress known in a certain frame, and then we can deduce the state of stress in any frame that is rotated with respect to x-axis by an angle theta. Now let us see some additional properties of interest. So for example, if you want to determine what is the point corresponding to the maximum value of sigma x prime, if you draw the circle that we mentioned, okay, we say that all state of stresses can be plotted on a circle. From this circle, it's clear that the maximum possible stress is at this level. And this point is located on the x-axis. X-axis here will represent sigma x prime, and y-axis will represent tau x prime, because we have seen that the relation tau x prime is y prime. We have seen that the relation between sigma and tau satisfies the relation of a circle. So we can represent all point of stresses on a circle. And we selected the horizontal axis to be sigma x prime and the vertical axis to be tau x prime y prime. We represented the center. We said that the coordinates of the center, sigma average, is sigma x plus sigma y over 2. And the radius also was already determined, as we mentioned before. The radius is the radical sigma x minus sigma y over 2 square plus tau xy square. So now if we draw our circle, we can observe that the maximum stress, possible stress, is at this point, which we call A. This point is on the sigma xy prime axis. So it's characterized by a shear stress of 0. And then for the minimum possible value of sigma, as you can see here, the minimum possible value of sigma is the point on the left of C and also on sigma x prime axis. So you can say that this will correspond also to a shear stress of 0. Now, it's clear from the figure that we can easily calculate sigma max, sigma minimum, because sigma maximum is simply sigma average, which is the coordinate of the center, plus the radius r. And sigma minimum is sigma average minus radius r. So knowing the value of the average, which is sigma x plus sigma y over 2, we can deduce what is the maximum possible stress that we can reach by doing, of course, by considering a certain other plane than xy. Okay, now the question is how to find this plane, how to find the orientation of this plane relative to xy frame. Then what we have to do then is to say, if I want to determine what is the angle of rotation that will allow me to find the maximum and minimum state of stress, I go back to my figure. I say I know the stress state at x and y. And from my circle, I can deduce that sigma max, sigma minimum values will be sigma average plus r and sigma average minus r. But to know they correspond to which axis, x prime, y prime, I should use my equations. What is the characteristic at the minimum and maximum stresses, normal stresses? The characteristics, as we can see in the figures, that the 2 points A and B are on sigma x prime axis. So this will correspond to a shear stress of 0. And since we already developed the equation of the shear stress, let us solve for it. So we have demonstrated that the shear stress tau x prime y prime can be correlated to sigma x, sigma y, tau xy, and theta. So this relation should be equal to 0. And as you can see from this relation, if you take this term to the other side, and you divide sine 2 theta by cosine 2 theta, you get that tan of 2 theta p. Why we say p here? P stands for principal axis. We say that the axis corresponding to maximum and minimum normal stresses with shear stress 0 are called the principal axis. Okay, and to locate these principal axis, we solve for tau x prime y prime equals to 0. As you can see, tan of 2 theta principal is equal to 2xy over sigma x minus sigma y. So in this way, you will be able to find the orientation of your principal axis. When you solve this equation, you will get 2 possible solutions, okay? Because you know that whenever we do tan, you have the solution can be alpha plus, or here 2 theta p equal to a certain angle alpha plus k pi. Okay, so let's say here plus k pi, taking k equal to 1. Okay, because if we take multiples of 1, 2, 3, you will go back to the same axis. So it's alpha. The first solution will be alpha, and the second one will be alpha plus pi. So this means that 2 theta will differ by pi. The 2 angles corresponding to sigma max and sigma minima, 2 times this angle will be differed by pi. So the angle will be differed by pi over 2. This means that if I determined one possible solution, which is alpha, okay, which is, sorry, theta p, the other solution will correspond to theta p plus 90. Okay, so of course it's expected that because here the 2 possible solutions of 2 theta p will have a difference of angle of pi, then the 2 possible solution for theta p, so theta p solutions will be, let's say, alpha over 2, and the second solution, so this is theta p1, and theta p2 will be alpha over 2 plus pi over 2. So the axis xp and yp, x prime p and y prime p, will have a difference of angle of pi over 2. Okay, so alpha over 2 plus pi over 2. So as you can see here, once I determine the orientation I should rotate from x to x prime, the orientation I should rotate from x to y prime will be theta p plus 90. And then I will deal, my principal axis will constitute a frame of axes that are perpendicular, x prime and y prime. And once I calculate theta p, I can say that along this axis, if I take an element around point Q in this frame, it will be characterized only by normal stresses, because shear stresses will be 0. And the normal stress to this face is sigma x prime maximum. The normal stress to this face is sigma y prime maximum. And I don't have shear stresses. Shear stresses are equal to 0. Now, what about other characteristic points corresponding to maximum shear stress? So now we have solved for state of stress corresponding to maximum normal stress. Now, if you want to solve for points corresponding to maximum shearing stress, also we can easily determine this from the figure. If you look at the figure here, it's clear that the maximum shear will occur at these levels, at points D and E. And the value of shear is just equal to the radius of the circle. Okay, so we can say that the maximum shear stress is equal to the radius of the circle. Now, to solve for the directions corresponding to the maximum shear stress, then we should look at an equation. The equation is the following. As you can see, maximum shear stresses takes place for a normal stress equal to sigma of C. So sigma of C, which is sigma average, correspond to the normal stress when the shear is maximum. So to find the position, the relative orientation of axis corresponding to maximum shear, I can solve the equation that sigma x prime equals to sigma average. Then I have sigma, I replace sigma x prime by the function I developed for sigma x prime when we did the relation between sigma x prime, sigma x, sigma y, tau xy, and theta. The expression we derived together is the following. Sigma x prime is sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta equals to the value of sigma average is sigma y x plus sigma y over 2. Now, taking this term to the other side and rearranging, we have that sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta equals to 0. This will give us that tan of 2 theta s corresponding to maximum shearing stress is equal to minus sigma x minus sigma y over 2 tau xy. And if you do a small comparison between the two formulas you obtain, you have that tangent 2 theta s is the following, while the expression we got in the previous slide for the angle of orientation of principal axis tan 2 theta p is equal to 2 tau xy over sigma x minus sigma y. So if you compare these two expressions, when you multiply tan 2 theta p by tan 2 theta s, you get minus 1. So if we do tan 2 theta p times tan 2 theta s, we get -1. And we know that mathematically, if we have two angles where the product of tangent is -1, then we can say that these two angles, the summation of these two angles is 90 degrees. Okay, so we deduce that 2 theta p 2 theta p plus 2 theta s equals to 90 degrees, and this means that theta p plus theta s is equal to 45. So we can deduce that the angle between the principal axis and the shear, the principal axis corresponding to maximum normal stress and the axis corresponding to maximum shearing stress, is the difference between angles of these axes is 45 degrees. Okay, now if we do the analysis on this figure here, going back to this figure, if you want to draw theta s, okay, then we can say we can solve for 2 theta s as we did before. So we get two possible solutions for 2 theta s. 2 theta s can be equal to beta, and also 2 theta s is equal to beta plus pi. So we can say that the two possible solutions for theta s corresponding to maximum shear is theta s1 equal to beta over 2, and theta s2 equals to beta over 2 plus 90. So also here we can say that the two directions corresponding to maximum shear stress are separated by an angle of 90 degrees. So now, if you want to present this axis, here you have a minus. So the angle theta s will be an angle of rotation in the negative direction, where you go from x to x prime in the negative direction. And the second axis corresponding to maximum shear will be theta s plus 90. So this is theta s plus 90. And if you represent on the same graph the principal axis, you will see that, so let's say we found already theta p. So this is theta p. Then the summation of the absolute value of these two angles is 45 degrees. Okay, so because theta p, let's say, is positive, theta s is negative. But if we take theta p plus absolute value of theta s, we got then 90 degrees, is 45 degrees. Okay, so until now we can say that the principal axis are separated by an angle of 90 degrees. They correspond to the maximum normal stress. The axis corresponding to maximum shear stress also are separated by 90 degrees. And the axis of the angle of orientation from x to the principal axis x prime is doing an angle of 90 degrees, of 45 degrees, with the angle of rotation of, from x to the shearing stress that is maximum. So this is 45 degrees. So all of these properties, we're able to deduce them from the characteristics of relation between stresses. We have seen that we can plot them on a circle. This will help us into the analysis. And we'll talk more about the analysis of the circle in future slides. Now, let us do some examples to practice on this. In the following problem, for the given state of stress, determine the normal and shearing stresses exerted on the oblique face of the shaded triangular element shown. Use a method of analysis based on the equilibrium of that element as we done in the derivations. So sometimes if they force you to use derivation methods, you cannot use the relations we developed before. You should go back to the analysis and say, all I have to do is, let us consider this triangular element. I did a cut here. I know the state of stress on these two faces. So now if I take this element, I can determine what is the state of stress on this face. So if we plot our triangle, we have three faces. We have that for this face, we have a downward shear force of 90 megapascal. For this face, we have both shear and normal stress. The normal stress is given to be 60 megapascal. And because here they gave you this stress here is 60. So due to equilibrium, of course, this one will be also 60. Okay. And we know that tau xy equal to tau yx. So if this is 90, then all of these shear stresses will be 90 for equilibrium purpose. So this is 90, this is 90, and this is 90. Okay, this will represent, this is, if we take this is x and this is y, okay, this will represent tau xy, and this is tau yx. And we know that they are equal because they should create opposite couples to maintain equilibrium on the square element. Now, if I want to use the convention of positive or negative tau xy, these are negative shear stresses. Why? Because as we mentioned before, for when I say tau xy, for this face, okay, for this face, you have the normal is positive along positive x, the normal vector. The normal vector is positive. However, the shear is along negative y. This is why if you want to put what is tau xy here, it's minus 90, not plus. Okay, it's minus 90. Here, no need to, because we will not use the formulas. If you want to use the formulas developed before, you should write that tau xy is minus 90. This is sigma, along x, no sigma. So sigma x equals to 0. And you have that sigma y, because as you can see here, it's causing compression on the face. So sigma y is minus 60 megapascal. So if you want to use the formulas developed in the course material to find sigma x prime, tau x prime, y prime, and sigma y prime, you should use these values for sigma x, sigma y, tau xy, and you will use an angle because we rotated from x. This is x, and this is x prime. We rotated from x to x prime an angle of 30 degrees. So theta here is 30. So you can use the developed formulas before by plugging theta by 30 degrees, sigma x 0, sigma y minus 60, and tau xy minus 90. You will obtain the same result that we'll do now, because they asked here for another method. They asked to do the method of analysis developed before for equilibrium condition. So now we will not use any formula. We'll do just the derivation together. We take the element, we put all forces, all stresses acting on it, and we relate areas. So if this is if I call this area A, because I have the same width for all my sides, for all my faces, then I can relate areas, because this length here is, if this is L, this is L cosine 30, and this is L sine 30. And as we mentioned, we have same width, so I can relate also areas. This area is cosine A cosine 30. This area is A sine 30, and this area is A. So now I can represent my forces. On this face, I have a normal force sigma times A shear force tau times A, and I have a downward shear of 90A sine 30. Here we have on this face shear and normal forces, so it's 90A cosine 30 and 60A cosine 30. Now, all I have to do is to do the balance. I decompose into x and y directions, and I say that sum of forces along x is 0, and sum of forces along y is 0. Now you can take, if you want, any directions, and you can project on x, y here if you want. You can project on these two directions, or you can project on these two. It's up to you. You will get, whatever you do, you'll get the same result. Okay, because at the end, sum of forces as a vector is 0. This vectorial relation can be projected on any two axes. You can project on x, y. You can project on x prime, y prime. The advantage of projecting on x prime, y prime is the following. So here you can take, for example, you can, because you know that the shear is down, you can take the axis x prime like this here, and the axis y prime like this. So since you want just to determine the values, you can take any directions of, since you are not using a formula, you can use any direction you want. And then when you do the projection, you should respect the directions you selected. In this problem, I selected the perpendicular to the face and the downward direction like this, because tau is downward. Okay, but you can select, of course, the upward direction and say when you do the projection, it's minus tau times A. And why is I selected these directions? Because when you do sum of forces along this one, you don't have tau, a projection of tau, because it's perpendicular. So then from this first equation, you can get sigma. And from the second relation, so you have decoupled relation. This one will give you sigma, this one will give you tau. But if you projected on these two directions, x and y, instead of having decoupled relations, you'll have projections of tau A and sigma A on x and y. So you solve two equations with two unknowns. And of course, you'll get at the end the same result. So here you can select any frame you want and do the projections. And at the end, you will obtain your two unknowns. Okay? So let us start first by projecting on this direction. As we can see, you have plus sigma A. For this force has a downward projection on this direction, and the angle here is 60. So or you do cosine 60, or you do sine 30. Okay, so here for this force, it's minus 90A sine 30, which is the value of the force, times cosine 30. Now, for this one, for this component is doing an angle of 30 degrees with this direction, but because we considered the 30 degrees with this direction, so with the other direction it will do an angle of 60. So this angle is 60 degrees. So or I do cosine 30, or I do sine 30, cosine 60, or I do sine 30. And from my figure, we can see that since I have the direction, this is my positive direction up, and I have the force will have, if I project it, will have a negative projection, this one, and the angle is 60 degrees here. So as we mentioned, we can do cosine 60 or sine 30. So it's minus 90A cosine 30 times sine 30. Now for this force, This force has a positive projection on the direction we are considering, and it has an angle of 30 degrees. So the angle here is 30. So you will do a plus 68 cosine 30 times cosine 30 equals to 0. This equation will directly give you the value of sigma. You can do the same procedure in the other direction. So just you have to do projection of forces, okay? And this will give you the value of tau. So here, if you want, we used the same methodology of projection of forces to determine the state of stress on this face without the need of applying a formula, because we went back to the concept analysis and we found sigma and tau on this face. Another problem, for the given state of stress, determine the principal planes and the principal stress. So here, whenever you have such cases, you can use formulas developed in the course material. So they gave us an element. This element is subjected. This is the case of plane stresses. You have, if I call this this is x, this is y. I have that sigma x is plus 28 because it's tension. Whenever enormous stress is positive when it's cause tension, it's negative when it will cause compression. So sigma x is plus 28. So this is 28 and this is 28. Sigma y is plus 140. And now what about tau? As we mentioned before, you look at this shear stress. Okay, this is tau xy. If you consider tau xy, you have the normal is along positive x, but this shear is along negative y. So tau xy here is negative. This is why I put minus 42. The shear stress tau xy to be positive on this face should be up, because in this case the normal vector to the face will be positive x and the shear will be oriented along positive y. Since it's the opposite case here, so we put for tau xy minus 42. And now we want to determine first the principal planes, so we should locate them on this figure. Then all we have to do is to apply the formula developed in the course material, which is tan of 2 theta p equal to 2xy over sigma x minus sigma y. We just have to plug in values. We get 2 theta p, and then we can divide by 2 to deduce the value of theta p. And as I told you, we select two values, and the difference between these two values is 90 degrees. So your calculator will give you 2 theta p 36.87. You divide by 2, you say that theta p is 18.43 as a first solution. I add a plus pi over 2 to get the second solution. And now I can present this axis on my figure. This is my x-axis. If I rotate an angle in positive direction, here is the counterclockwise direction. If I rotate an angle of 18.43 degrees, I get the first principal axis. As we said, principal plane corresponds to maximum normal stress. So this is my, if you want, x prime principal. And to deduce y prime principal, I just rotate 90 degrees. So this is y prime principal. Okay, and now they want us also to determine what is the value of the principal stresses. As we discussed together, sigma maximum, sigma minimum can be obtained as sigma max is sigma average plus the radius of the circle. So I just have to apply this formula, sigma average plus radius of my circle, and sigma minimum is sigma average minus radius of my circle. And here, you know that sigma average is given by sigma x plus sigma y over 2. The radius of my circle is given by radical sigma x minus sigma x minus sigma y over 2 square plus tau xy square. So I can do my calculations to find sigma maximum and sigma minimum. So this is a pure application of the formulas we have developed together. Another problem, for the given state of stress, determine the orientation of maximum in-plane shearing stress and the corresponding normal stress. Okay, so also here, it's a practice for the case how to determine the maximum shear stress. The first step will be to determine the values of sigma x, sigma y, and tau xy. So again, we go back to the figure. From this figure, we have first, for along x, we have tensile stresses. So sigma x is plus 63. And concerning sigma y, okay, so you have here compressive stresses along y. For this reason, sigma y will be minus 42. Now, if you look at shear stresses, this is tau xy. So here, tau xy is positive because for this face here, for this face, you have the normal to the face is positive x, and you have tau along positive y, so your shear is positive and is equal to plus 28 megapascal. Once you determine the state of stress, now you can calculate all your angles. Okay, you can find the values of your angles. So all you have to do then is the following. You consider first, if I look at, I want to find the angle of the orientation of the plane of maximum shear stress. This is why I should solve for theta s, which is the angle corresponding to maximum shear stress. And from the developed course material, we have tan of 2 theta s is minus sigma x minus sigma y over 2 tau xy. Keep in mind, these are algebraic values. So now when you plug in, sigma x is plus 63, but sigma y is minus 42. This is why minus minus will give you plus. So tan 2 theta s is minus 63 plus 42 over 2 times 28. And you will get your angle. 2 theta s is minus 61.93. So you can find the two corresponding solution for theta s, which is minus 30.86. And plus, if you add to it plus 90, you get the second axis. So if I want to present here in this figure the orientation of axis corresponding to the maximum in-plane shearing stress, I have the following. I have first, I rotate, whenever you get a negative result, then you rotate from x-axis into the clockwise direction. This is your x-axis. So you got a negative result for theta s, you'll rotate in negative direction. So this angle in negative direction is 30.86. And so this is if you want x prime maximum shear, so this x prime s, and y prime s is the one that is perpendicular to it, so this is y prime s. And you can deduce from here now the principal axis, because as we mentioned together before, the angle between maximum shear axis and maximum normal stresses is an angle of 45 degrees. Okay, so if this is x prime s, so x prime p is like this. This is x prime principal, and the summation, so if I go from this one to this one, I have a total angle of 45 degrees. So this is, because this is 30.86, this will be 45 minus 30.86. 30.96. And I can now deduce y prime principal, which is perpendicular to x prime principal. Okay. So this is how you can determine, once you determine the orientation of maximum shear, you can deduce the orientation of maximum normal stress. Okay. Now, they also want you to find the corresponding normal stress. Okay. So of course, first for the maximum shear stress, it's equal to the radius of the circle, and the radius of the circle is related to sigma x, sigma y, tau xy by the following relation. Tau max equals to radical sigma x minus sigma y over 2 square plus tau xy square. And now to find the corresponding normal stress, all you have to say is I can calculate the value of normal stress for maximum. If you remember, when we considered the circle, we said that the the points corresponding to maximum shear will take place at sigma equal to sigma average. So the corresponding, which is sigma of C. So the corresponding normal stress is simply equal to sigma average equals to sigma x plus sigma y over 2, and you can calculate. Okay, so the maximum shear is equal to the radius of the circle, and the corresponding normal stress for this orientation of axis will give you a normal stress equal to the value of sigma average at C. So pay attention, when we have maximum normal stress, the shear is 0. But when we have maximum shear stress, the normal stress is not 0, it's equal to sigma average, which is sigma x plus sigma y over 2. Another problem, we have two members of uniform cross section given by 50 times 80 millimeter that are glued together along a plane AA that forms an angle of 25 degrees with the horizontal. Knowing that the allowable stresses for the glued joint are sigma equal to 800 kilopascal and tau equal to 600 kilopascal, determine the largest centric load P that can be applied. Okay. So first, let us do the analysis of this problem. In this problem, they want us to determine the maximum load P to not exceed the stresses sigma and tau in this section. So for the glued section here, they mentioned for us what should be the value of sigma and tau. So here, if you want, they gave us sigma x prime, sigma x prime tau, x prime y prime. And we want to do the analysis in order to find what is maximum P that can be applied. Okay. Now, the idea is, under the effect of P, if I take a section that is like this, it's parallel to the ceiling level, let's say. Okay. So I consider that for a certain cut, if I do a cut here, I just have this is x direction and this is y direction. If I take an element along this plane xy, what can I say about stresses? It will only be subjected to a normal stress, because if I do a cut anywhere here, okay, anywhere here, I will have just P from this side. So as normal stress, it's P over A, and P over A from the other side. So I have tensile stresses. I don't have shear stresses along this section. However, if I consider the glued section, because it has a certain inclination, in this glued section, I have both normal and shear stress. And I can relate the state of stress in this section to the state of stress in the glued section. How to do this? First, I say, let me determine the angle of rotation between the XY section and X prime Y prime section. If I illustrate the state of stress in XY plane, as we mentioned together, we have only stresses along Y. So we have, and these are tensile stresses. This is why sigma Y is plus P over A. And sigma X is 0 because you don't have any normal stress along X, and you don't have any shear stress along along the faces. So tau XY is 0, sigma X is 0. You only have sigma Y, which is P over A. Okay? Now, from the other side, whenever this is your X, okay? Now, your glued section is here. The glued section, according to the figure, is here, okay? Doing an angle of 25 degrees like this, okay? This is 25. So if I consider this axis as X prime, and this axis as Y prime, okay, I can say that on the glued section, I will have sigma X prime, and I will have tau X prime Y prime. Okay, now what is the angle of rotation from X to X prime? As you can see in the figure, it's 90 minus 25 degrees. So in this case, the value of theta is 65. Okay, so theta is 65 degrees. And now, accordingly, I can calculate the values of sigma and tau in my section of interest, in my glued section. So sigma and tau in my glued section can be calculated from knowing the values of sigma x, sigma y, tau xy, and the angle 60. I just have to replace in the formulas developed in the course material. From the formulas developed in the course material, I have that sigma is equal to sigma x cosine square theta plus sigma y sine square theta plus 2 tau xy sine theta cosine theta, replacing by the values of sigma x, sigma y, tau xy, and theta, I get the value of sigma. Okay, and I get a function of P because P is unknown. I want to design the value of P that will not, I should select a value of the maximum value of P to not exceed the normal stress in the glued section and the shear stress in the glued section. So the first step was to express P function of sigma. So I got first P function of sigma from this expression, okay? And since I have the allowable value of sigma given to me, I just have to replace it. This will give me the first P1 maximum, the first maximum value of P that is allowable, okay? Now I move to the second step. I express now tau function of sigma x, sigma y, theta tau xy using the formula of the course material. I plug in values, so I get tau function of P. And now, because I have the allowable stress tau, what is the maximum possible value of tau? I replace tau by the allowable value, and then I get P max 2. So P max 2 is A times tau over sine 65 cosine 65. And then I get another value for P. And as usual, because I have to design for P max and I got two values, I will select the minimal one between the two to satisfy both constraints. So here P should not exceed 3.9 kilonewton, and I can deduce that the shear condition is more critical than the the stress condition, the normal stress condition. So this corresponds to the condition to not exceed the maximum normal stress, is more critical than the condition of not exceeding the maximum shear stress. This is why if failure will occur, it will occur by due to normal stress failure, not due to shear failure. Okay, so here I should not exceed 3.9, because if I exceed 3.9 kilonewton, I will have a rupture by tensile forces. Okay, so this is the design. In this problem, we have to combine our knowledge of design and how to deduce the stress, the state of stress in any orientation, knowing the state of stress in a certain orientation X and Y.